Welcome to the world of kinematics and robotics. This is the first episode in this series where we'll be covering some basic mathematics and physics. To start with, we will cover some basic trigonometry and very basic definitions. For the most part, I will be face off in this episode. So I would like to bring a workspace where I can depict what we are going to be talking about. So trigonometry is actually a branch in mathematics that is the study about triangles and the relationship between its angles and its sides. So let me draw a right-angled triangle here. For definition, I'm going to actually define what these mean. The hypotenuse here that is marked is the longest side in a right-angled triangle. It is the side opposite to the right angle. The angle marked here as theta is the angle between the hypotenuse and one of the sides, and here it's the adjacent side because it is adjacent to the hypotenuse here. And the side that is opposite to the angle theta is called the opposite side, aptly named so. So for some definitions here, the sine of this angle is defined as the ratio of the length of the opposite side to the length of the hypotenuse. The cosine of that angle, cos theta, is defined as the ratio of the adjacent side length to the hypotenuse length. The tangent of that angle is defined as the ratio of those two, which is the ratio of sine to the cosine of that angle, which by definition and by mathematics will give you that it is the ratio of the opposite side to the adjacent side. So this is something that I want to make sure that we all remember and understand, and hence I'm refreshing your thoughts if at all. Some other basic trigonometric formulae are things that I'm going to be listing here. Please take a moment to pause the video and note these down. These are formulae that we will use throughout the series, and I would strongly suggest that you make a note of all of these formulae. Let's discuss vectors. What really is a vector? I think the textbook definition would go something like it's a physical or a mathematical quantity that has some magnitude and a direction. I think it is very important that we understand what a vector really means. And I would like to define what a scalar is and also define analogous vectors to those so that we have a thorough understanding of what vectors are. So a scalar is actually just a number. It does not have any direction. For example, the length of a side of a notebook or the mass of an object, let's say a ball or a book, or let's say you're driving down the highway and at a speed of like 60 kilometer an hour. So what that means is you're driving at 60 kilometer an hour. It doesn't tell you anything else. So if you're driving north, then it's different. If you're driving south, you still have a speed, but that's not a vector. That's a scalar. What a vector really is displacement is a vector. If you had to say that I am driving on the highway at 60 kilometer an hour heading north, so that is a velocity vector. And if you were to measure the displacement from a point A to point B, you can measure the distance. But if you're going from A to B, that means you're actually saying that in this direction, I'm measuring that distance. So that's actually a displacement. A force is actually also a vector. And to give an idea, force is actually in physics, it's the rate of change of momentum. Otherwise, also the more common verbiage is force is mass times the acceleration. Mass actually is a scalar, as I had mentioned earlier, how much, let's say the mass of an object is something, X kilograms. That actually means that force is a scalar times a vector, which is acceleration. Acceleration is defined as the rate of change of velocity, which is also another vector. So force in reality gets its direction from the acceleration, but gets its magnitude magnified or multiplied by the scalar, which is the mass. So what do we actually call vectors to be? A simple vector representation can be on a graph, and it has a starting point and an ending point. And you specify the direction in which it goes. Vector quantities also have a magnitude, mostly measured in its length, and give it a direction. There are things called unit vectors, and these are vectors which have a magnitude of 1. What does this actually mean? So for definition, let me actually bring a 3D system. The world we live in is 3D. So let's bring a workspace here and a right-handed coordinate system. What this means is in 3D, if you were to keep your right hand, forefinger, middle finger, and your thumb indexed at 90 degrees to each other, the forefinger is the red axis, which can be called x-axis here. The green axis is the y-axis, and z is your thumb, that is the z-axis. The vectors I, j, and k are denoted to be unit vectors that act along x, y, and z-axis respectively. And these have a magnitude of 1. They don't have to be only on this, right? I, j, k are on x, y, and z. But unit vectors can act along any direction. If there's a vector between I and j and on the xy plane, that can have both I and j quantities, but there can be a unit vector acting along that direction as well. So we will get to more of those, but note that a unit vector is a term that denote its magnitude only and not the direction. We will get to the direction cosines of it later soon, but for now, it's something that we need to know. So we saw some vectors in 3D space, but let's actually look a little bit about vectors in 2D first, get a thorough understanding, and then we can discuss and extend these ideas in 3D as well. So for representing vectors in 2D, we need some very basic computer tools for plotting. So what's shown here is a grid that is just using Microsoft Excel for plotting. It's important that we have a square grid and it is equal in its length. Plotting in a grid that is square is very, very important for visualization. And I cannot stress on this more, because if your x-axis is skewed in any way, if it's elongated, and if your axis is not square, you will find that your plots look funny. So it's important for that. So let's see. A vector generally has a tail, a head, and a magnitude and a direction. What does that really mean? So let's actually bring this workspace more usable. Let's plot an x-axis. Let's plot a y-axis. So this is our x and y-axis. And let's see if I click on that. Let's bring an origin. So that's the origin point. So let's say somewhere around here, I mark a tail point, and then let's draw that vector out. So here, that length of that particular line segment with an arrow, that's how we define vectors in plotting. That is often denoted as the modulus of r vector, which is r here. And the angle theta, let's see, how do we define this correctly? Let's extend these lines and draw a horizontal. An angle of that vector is defined as the angle from the horizontal to that heading direction. It is not an angle between the horizontal and the vector. It is the angle from the horizontal to the vector. This is often misleading and left out. It is important that we follow this convention And it's a convention. We follow this throughout this video series, and we will use this in 3D as well. So counterclockwise is often taken as positive. So that is what we will be following here. And let's see what are the other more common things that we see. Oh, yeah. OA, OB, and AB. These are like just thrown out in the dark when we were studying vectors. But what does that really mean? And we say, oh, AB vector is OB minus OA vector. Also, if we do the opposite, rearrange this, we say OB vector equals AB plus OA. What does this really mean? Let's get something clarified here. All right, what you see here is the same plot that you saw. Now here we have a vector that is called AB, and where it has a tail. Let's call the tail as the starting point, and it's at 1.6, 2.6 in a coordinate. But what that coordinate actually means is I'm moving 1.6 in the x direction and then going in the y direction by 2.6. That's where I get to that vector. That is a starting point, and then I move by some length. The r value that you saw right now, it can be changed. Right now it's a 2. It can be made into like longer. Or let's say I want to change the direction. I can change the direction. I can make it 0, or I can go in the negative direction all the way. I can keep going round and round, but you get the point. So this essentially is a vector. So if I move by the length times in that direction, I get to a point. That point is the AB vector point. Here I call it as it's computed to be 4.3577, 4.91403, etc. So what does this mean? AB vector. So that end point is actually the final coordinate, just final coordinate of that point, if you will. And there is a start point. So if I move from here to that point, and from there to that point, I get from here to that point. That's exactly what it means. So what it means is, let's say I have this point as A and that point as B. And let's say the origin is O, OA, then AB. So OA plus AB, we will get this relative to O, which is OB. What that really means is, let's bring the other two vectors. So I'm going to bring the OA vector and then OB vector. So that's what it means. So what it means is, now I have this program in a way such that I can just change this. I can change the length of it, and everything changes automatically. So what we saw there was nothing but addition of vectors. So you just go from one point to another, and from there to another, and you get the original point. That's just a triangle law of vectors. That's exactly what it means. So if you go along a vector by its magnitude in that direction, and you go from that to another vector along another direction, the endpoint is the sum of these two. That's what triangle law is. There is something called parallelogram law of vectors, which I will cover at a later point. Parallelogram law is something that I think you should go look for references for now. We will not use this immediately in this episode, but we will definitely revise this in a future episode. There's another form of vector called Euler form of vector. What this means is R vector is defined as the modulus multiplied by the e power I theta. That e power I theta is the Euler form. It's cos theta plus I times the sine of theta. This is just another way of representing a vector in its magnitude and direction directly, rather than I, j, k. So let's actually look at what this really means, right? There is a real part and an imaginary part. Let's bring our workspace back. Now let's draw instead of an x-axis, I'll call it the real axis, right? And let's go draw an imaginary axis. Let's draw a circle. Let's first get the origin. Oh, let's draw a circle. This is the Eulerian circle, if you will. So with a radius of unit 1, and of course in the imaginary axis that will be I, and this will be minus I, and that will be minus 1. So if I were to draw a vector r whose magnitude is 1, it's very important that you notice its magnitude is 1, and theta is the angle it makes with the horizontal. That is r, which is 1 times the cosine of theta, and that will be 1 times the sine of theta. And that point vector in this space is defined as cos theta plus I sine theta. And if this is scaled up, when I say scaled up, it's very important to note the scale is a scalar. It's r cos theta and r sine theta. That's what it means. So this is the Eulerian form. We will use this a lot in our series. What else can we cover about vectors? That's right, dot product. Vector dot product in its definition is the dot product of two vectors represented by a dot in between them. It is defined as the modulus and magnitude of one of them and multiplied by the magnitude of the other one. And the theta is here the angle between and not from one to another. It is between. Only in the case of a dot product we look at the angle between and not angle from one to another. Theta is the angle between the vectors and generally referred to as scalar product. It results in a scalar value. It doesn't result in any vector. You see that we've taken a magnitude and magnitude here, and cos of an angle is going to be somewhere between minus 1 and plus 1. So that's what it's actually going to be. All cos of minus theta is also cos theta. So you will get it as just a scalar value. It's often referred to give the projection of one on another. This is irrespective of the order, and when I state that, that already means that it's commutative. But what does that really mean? Let's actually look at that. Let's bring our workspace back. Let me draw a vector A. Let's draw another vector B. If let's first get an angle, or let's extend these first. Yeah, let's say that is the angle. If I were to shine light from above at an angle that is perpendicular to a vector, then we are projecting that vector B on vector A. So if we were to just look at what this value would be, it would just be the magnitude multiplied by the cosine of that angle. So what does it mean irrespective of the order? Let's see if I were to shine a light from there, but to perpendicular to the B vector. See here that they don't have to intersect and or fully be projected, but I can get that distance as A cos theta. So if this is B cos theta and this is A cos theta, and if I just multiply that by B and multiply this by A, I get the same values. So that's what means when it is commutative. When 3D vectors are represented in the IJK form, then it's very simple that their dot product is simply the algebraic addition of the product of their respective coefficients. We will cover this in a later episode and we will definitely use it a lot. So let's just absorb this for now. Note that dot product between two vectors is defined as the projection of one on another. That's what it means. So let's look at the practical example of a dot product. As I had mentioned, we will use this a lot throughout this series. And we saw that if we were to move in the x direction and we have an r vector, r projected onto x is r cos theta, and r projected onto y is r sine theta. But let's have a used example, but with a different view. what you see here on screen is exactly what we had as AB vector, OA vector, and OB vector. So now let's remove that OB vector and let's actually change it a little more. Let's add some fluff to it. So what you see here is just with a different view where we had the AB vector and the OA vector. But I was able to rotate the AB vector in many directions like that. Let's say if I were to rotate the OA vector also, but AB rotates with it, what does this actually mean? This, what you see here, is nothing but a planar elbow. This is a robotic system with a 2 degree of freedom. We will know a little more about these degrees of freedom very soon. But what this means is the OA plus AB vector was OB vector. So if I move from O to A and A to B, my OB is just the end point. That is actually nothing but the triangle law of vectors. Now that was nothing but it was practically a SCARA robot arm. And there are some implicit constraints, but we need to look at it a little deeper. So it is a planar mechanism, which means it is in plane only. And there are degrees of freedom that we will look more into this. A plane in general has only 3 degrees of freedom. So if I were to bring an object in 2D space, this object can have a translation in that direction, a translation in that direction, or a combination of two. So X and Y together can move, but it can also rotate about that axis. So that essentially is its degrees of freedom. So it's a translation in X, translation in Y, and rotation about the Z. So that's 3 degrees of freedom in a planar system. And it's got some constraints to it. We will discuss more about this. And very importantly, we are studying rigid bodies where we do not take into account the deformation of the object when it is actually being studied for kinematics. So let's look at a little more on the physics side of it. We have a displacement vector, S vector. Generally, that's the alphabet used for denoting displacement vector. Velocity is the rate of change of displacement, that is ds. It's a time derivative of ds over dt, essentially that's what it is. Acceleration is defined as the rate of change of velocity, so it's a time derivative of the velocity vector, or it's the d squared s over dt squared of essentially the double differentiation of the displacement vector. Force, as I had mentioned in the start of this episode, is a rate of change of momentum. So what that means, it's a time derivative of momentum, and as I had mentioned, m is actually if your mass doesn't change, then rate of change of momentum is essentially m times dv over dt, and that is how you obtain force is mass times the acceleration, and mass is a scalar here. In truth, if your mass also varies with velocity, which the moment you get out of you go towards the speed of light, it is said that your mass increases, and as well as if you accelerate faster, your mass increases. So then it's it's a different change. Rate of change of momentum becomes very different, but we'll stick to this domain for now, where mass does not change too much when you're spinning. And work done is the dot product of the force and the displacement. What this actually means is that a component of force that causes a displacement of s in that direction of the force, that is the work done. Essentially, how much projection of the force actually causes it on the displacement. That is what work done is. This is a proper application of the dot product of vectors. So if we look at the displacement vector in the Euler form, let's say S equals, we'll call it R, and it has a magnitude and a direction R e to the I theta. I'm omitting the modulus symbol here. We'll just call it R here for now. Let's differentiate this with respect to time. So we have to differentiate by parts. So R e to the I theta can be differentiated like what is shown here. This just means I keep R constant and then have e to the I theta differentiation. Then I keep e to the I outside and then I differentiate R. What this actually means is I get two different velocities, the d over dt of e to the I theta and then d over dt of R. A vector can change in length and direction if it changes in length and direction. So what does that mean? Those result in two things. One is an angular velocity and the other one is linear velocity. This is actually what we will see soon. Note that the angular velocity and linear velocity, there are two terms here for the velocity. If I differentiate this further, what are the items, what are the terms that I will get? Just think about it. We will actually talk more about this in the next class, in the next episode, I guess. But think about it, what all we will obtain by differentiating this vector again, this velocity vector. We will be seeing a lot more in the future episodes. We will see acceleration types. So what I had mentioned about differentiating the velocity vector, which has two units already, two terms, we will get different types of acceleration, which we can see. We will also know about cross products, its significance, especially in vectors, and its applications. Principle of moments. This is examples that we will see about as to why the sum of the clockwise moments and anti-clockwise moments, how they are equal, and we can figure out how to find forces based on that. We will study a lot about planar kinematics. We will understand the Grubler equation, the mobility equation. We will understand closed loop kinematic chains. We will mainly study what those mean. We'll study vector loop equations. We will study four-bar modeling. This probably will be its own episode. And then we'll study about rigid body guidance in 2D. There are some simple quasi-static force calculations we will do. We will study open loop kinematics chains. Like what you just saw as a planar elbow, we'll study a little more on that both in 2D and in 3D. That will be the end of this episode. Please don't forget to like, comment, share, and subscribe. I will look forward to any questions on the comment section and I can help as much as possible. You'll be able to do a lot of what you see here on screen. These are actual vector and path planning that's happening with a planar elbow, and we will study a lot more of how to apply all of this in real life. Cheers.